Hello. So now we're moving on to really the heart and soul of what Unit 8 is all about, and that's weak acids and weak bases. Because with strong acids and strong bases, remember that the arrow was a full arrow, they did not reach equilibrium. But when we're talking about weak acids and weak bases, we will be doing equilibrium, which means we'll be doing those ice charts again. So you can read through the topics. So we're starting with 8.3, and we will also do in this section some work with 8.7, which is about buffers. So first of all, for weak acids, we are going to use this formula an awful lot. This one right here. Oftentimes weak acids have really complex formulas with them. And so I will often just abbreviate, instead of writing out the entire chemical, I'll just write HA, meaning the weak acid. And it will react with water. And remember, acids are proton donors, so it will lose a hydrogen. It will donate a hydrogen to the water. And on the product side, we'll have H3O plus and A minus, or the conjugate base. And that H3O plus is what we're going to use to find the pH, because it's the negative log of that concentration. So we need to find the, basically that this is the guy that we need to solve for. We need to solve for that in order to find the pH of a weak acid. And that's going to be related to Ka. So just as we had equilibrium constants for regular reactions, we're going to have equilibrium constants exclusively for acid-base reactions. And if it is the species acting as an acid, we are going to say K with a subscript of A. And then we'll learn later on we do the same thing if it's K, if it's a base, subscript B. So here's a table of some common compounds that they're not common at all. They're common weak acids that we're going to use a lot. A full table of a whole bunch of weak acids and their equilibrium constants is in Appendix D, I think. And I will give that to you in class for you to look at, like for doing homework. You'll look at the Kas and you'll notice that they're all very low. When we were doing KCs and KPs, sometimes they were like 50, 59, like they were numbers that were greater than 1. Remember, this is essentially the ratio of products over reactants. Weak acids do not completely dissociate, so we would be thinking that it's a small number. And so this is, we're going to go through some sample calculations. The first one is calculating Ka from pH. And so it says a student is prepared 0.1 molar solution of formic acid and found its pH to be 2.38. Calculate the Ka at this temperature. Remember, temperature is going to change the equilibrium constants. So write a balanced chemical equation for the compound acting as an acid. And again, you could write HCOOH, or you could just write HA. But you always need to show it reacting with water, or I will always show it reacting with water, and then donating a hydrogen to the water. So making H3O plus and HCOO negative. It's that last hydrogen that's attached to the oxygen that gets donated. And then what would be the Ka for this? Well, Ka would be the concentration of the H3O plus times the concentration of the HCOO minus over the concentration of the HCOOH. Okay? Concentration, I should put that in brackets. So then we go to an ice chart, because what we're going to need to figure out are basically all those numbers. So I write the chemical equation up top. So HCOOH plus H2O in equilibrium with H3O plus and HCOO negative. Now remember, water is a liquid, so I don't even need to worry about water in this. I'm just going to put an X through it all the time. My original concentration of the formic acid is 0.10, and these guys start out as 0. And I basically want to find all those numbers in that equilibrium row. I have one more piece of information that is really important. The question told me that the pH of that solution was 2.38. And I can figure out that that means that the concentration of the H plus, which is of course the same thing as the concentration of the H3O plus, that is 10 to the negative 2.38. 2 to the negative 2.38 is 0.0041. And so that meant that guy must have increased by 0.0041. And this guy must have also increased by 0.0041. And this guy must have decreased by 0.0041. So that gives me 0.0958 and 0.0041. Perfect. So what is the Ka? Now I just plug in the numbers from the equilibrium row. 0.0041 times 0.0041 over 0.0958. And that is equal to 1.81 times 10 to the negative 4. Okay, so all these questions are going to be very similar to each other because they are going to all be about making an ice chart and trying to use what information I have to fill out the entire ice chart. The second half of this question is going to ask us to find the percent ionization. So remember that these weak acids do not dissociate very much. So we want to actually find out, well, how much did this guy dissociate? Did 50% of it actually react? Did 10% of it react? What percent? So you could figure it's the number of moles or the molarity of the ion over the total moles of the species, of the acid at the beginning before it reacted. So in this case, right, we know that it was 4.2 times 10 to the negative 3 was the moles of the ion. That's what the question reminds us of. And it started out with 0.10 molarity. And it doesn't matter if it says moles over moles because these would be in the same volume. When I divide those and then multiply it by 100%, I get 4.2%. And this is important. Generally, if the percent ionization is less than 5%, which in this case it is, then what I can say is the amount that it actually dissociated is negligible. So that means the X is negligible when subtracting from the acid. Basically, let me go back to the previous slide. This number right here, for most of the time in this, I would say all the time, from now on, we're just going to forget that that even exists. Because what we're going to notice is that to two significant figures, it's not going to actually make a difference in our answer. And it makes a big difference in terms of how hard the calculation is. So the AP test always assumes that in Ka, Kb, and Ksp, that is negligible. But Kc and Kp, it is often not negligible. So let's do an example here, and I'll show you what I mean by it being negligible. So to calculate the pH of a 0.2 molar solution of HCN. So when I always think, what do I need to calculate the pH? Well, I need to calculate the concentration of the H3O plus and at equilibrium. And how am I going to get that? I'm going to find that in an ice chart. So write the formula for HCN acting as an acid. So here's it reacting with water, donating a proton to water, and leaving its conjugate base. It tells me, the question told me that it was 0.20 molarity. Water, I always can just cross out, and these guys would be 0, 0. And this guy would go down by some amount, and these guys would go up by some amount. Right? They all have the same coefficient, and that's going to happen 99% of the time in this chapter where they're both going to be X and X. So this guy will, of course, be X, and this guy will, of course, be X. And what I'm going to assume from now on is that 0.20 minus X, that X is very small compared with the amount of acid that I start with. Not necessarily compared to 0, but compared with the amount that I started with. So this is sort of the weird thing. How can 0.2 minus some amount equal 0.2? Because we're calling that some amount much too small to make a big difference. So now I can plug it into the Ka formula, right? We know that Ka would be equal to the concentration of the H3O plus times the concentration of the Cn minus over the concentration of the HCN. I look up the Ka for HCN in the back of the book, and it tells me it's 4.9 times 10 to negative 10. And what does that equal? Well, x squared, because it would be H3O plus Cn minus over 0.20. I multiply, take the square root. I figure out that X, which is really the concentration of the H3O plus, is equal to 9.89 times 10 to negative 6 molarity, and then take the negative log of the concentration of the H3O plus, so the negative log of that, and I get 5.00. I'm choosing, we talked about this in the last chapter, right? But since this has two significant figures, this number that I used has two significant figures, then my final answer is going to have 2 digits past the decimal point. That's a little bit different than what we may have done in previous years, but with significant figures, but it's because of the logarithms, basically. So here is another practice exercise, and it's the mathematics is pretty much the exact same. The Ka for niacin is 1.5 times 10 to the 5th. What's the pH of a 0.01 molar solution niacin? Now, this is where, do I really need to look up the formula for niacin? No, I have no idea what it is. I'm just going to say HA, right? So some weak acid plus water will react and form an equilibrium with H3O plus and some random conjugate base. What are my initial concentrations? Well, I don't care about the water. This is 0.010, and these guys are 0. This guy goes down by some amount x. These guys go up by some amount x. Again, from now on, that minus x, this part right here, negligible. I don't even need to worry about it. Now it's pretty straightforward. Ka, which is 1.5 times 10 to the negative 5th, is equal to products over reactants, coefficients become exponents. X times x is x squared, 0.010, right? I solve for x, which is really the concentration of the H3O plus, and I like to write that down because it just reminds me, what am I solving for? This equals 3.87 times 10 to the negative 4, and I take the negative log of that, and I get 3.41. Again, 2 digits past the decimal point. Both numbers that I used in the problem had 2 significant figures. We're going to do lots of problems like that, so make sure that you understand how to set up the ice chart and all the math that I did there, like the concepts and the arithmetic. So just one last little piece before we start talking about weak bases is just to touch upon polyprotic acids. So we know the definition of polyprotic acids is that there's more than one ionizable or more than one hydrogen ion that can be donated. And every single time that you have a K, the subsequent K of the next hydrogen being lost is a lot smaller. So this is the weak acid H2SO3. And you can see the Ka is 1.7 times 10 to the negative 2. It says Ka1 because that is signifying that you're donating the first hydrogen. You can see this reaction is donating the second hydrogen, and the Ka2, or the Ka for that reaction, is just way, way, way smaller. Okay, so you'll have lots of practice with doing problems exactly like this in your homework and in preparation for the next test.